Welcome to ES 310 Lesson 20. Today we're going to extend the work we have been doing with relative velocities to the acceleration realm. And so we'll be looking at the finding acceleration of points on rigid bodies when information is known about accelerations of other points on those bodies. And we will also be looking at finding angular accelerations of rigid bodies. More information about this topic can be found in Hibbler's Dynamics textbook, Chapter 16, Sections 7 and 8. So as a quick review of where we are, we started looking at rigid bodies several lessons ago, and we looked at angular motion. We looked at some definitions, some standard kinematic definitions of angular velocity and angular momentum related to angular position and time. We looked at special cases where our angular acceleration is constant, and our equations look fairly familiar. They look like our linear equations except with angular variables instead. And then we looked at finding angular positions, velocities, and accelerations relative to fixed points. We looked at the absolute motion approach, which will only work if we have a fixed point and we can relate our angular and linear motion through the geometry of the system. And then we looked at relative motion, which is a more general approach, which relates the motion of point B to the motion of point A plus the relative motion between the 2 points. Today, this is the equation we're going to start with when we start talking about our acceleration. If we have an instantaneous center of zero velocity, so a point somewhere on the body or somewhere in the system, not necessarily on the body, but somewhere in the system that has a zero velocity, these equations simplify because VA doesn't exist, and so we can write VB simply as omega crossed with r. So to find the acceleration, we start with that last equation on the previous slide, and we take the time derivative. And so we're going to take the time derivative of the velocity of B, and we're going to get the acceleration of B. And the time derivative of the velocity of A, we get the acceleration at A. And the time derivative of the relative velocity between B and A gives us a tangential acceleration between B and A, and a normal acceleration between B and A. So if we look at our equations, or our variables, we've got the acceleration of point B relative to the ground, the acceleration of point A relative to the ground, the tangential acceleration of B with respect to A, which is alpha crossed with r of B with respect to A, so the position of B as measured from A. And then we have the normal acceleration of B relative to A, which is omega squared, so the angular velocity squared times r of B with respect to A in negative direction. And so the tangential acceleration is perpendicular to this distance. The normal acceleration is parallel to the direction RBA and acts towards the center. It's a centripetal acceleration. So the procedure for these is we're going to use the equations we used in the last lesson to find omega based on the knowledge about velocities, and then we're going to use that omega in the equations on the previous slides, along with the acceleration of A, acceleration of B, the angular acceleration of the system, and the position of B relative to A. And we apply then this final equation, which is our key equation for the day. So these problems tend to be much longer than problems we've seen so far, but not really all that much more complicated. And so we'll take a look at an example, and hopefully that will become clear. So let's start. In this example, we've got the wheel. The wheel is turning, and as the wheel turns, this bar also shifts its position, and the collar slides. And we're interested in the acceleration of the collar of A. We're given information about omega and alpha for the wheel, and some various other geometric information. So let's start by writing the equation we're ultimately going to solve for the acceleration of A. So we have the acceleration of A, which is a vector, is equal to the acceleration of B relative to the ground, plus alpha crossed with r of A as measured from B, those are both vectors, minus omega squared r of A relative to B. So that's our key equation. Now let's look at this and see what we can determine and how we can determine our unknowns in order to end up solving the acceleration of A. So first of all, we know the acceleration of A has to be in the horizontal plane. So if this is the I hat direction, that's the Y hat, J hat direction. This is going to be AA in the I hat direction. Positive or negative, we don't know. We're just going to assume positive for the time being. AB, we can't necessarily give us a direction, right? Because B is going to have a tangential part, normal part is moving. So we'll just leave it as a vector for now, and we'll work on solving that. And then we have plus alpha AB, which is the angular acceleration of this beam, or that bar, which is in the k hat direction, crossed with RAB. So RAB is the position of A relative to B, so it's that direction, right? We'll write that out. RAB is equal to, in the I direction, we go over this far, right? So it's positive direction, and that is 500 cosine of 60, right? This far is the same as this distance, or if this is 60, this is also 60 down here. So that's going to be 0.5 meters times the cosine adjacent of 60 in the I hat direction, positive. Then we're going to go up that far, right? All the way up there. That's going to be also positive, so 0.5 sine of 60 in the j hat direction. So that's our R direction, so we can write that in here. So crossed with 0.5 cosine 60 I hat plus sine 60 j hat. All right, then we have minus omega squared. We don't know omega squared yet, so that's omega AB and alpha AB, right? Times R again, so that's 0.5 cosine of 60 I hat plus 0.5 sine of 60 j hat. So that is our final equation. We need to figure out what all these unknowns are so we can plug them in and find AA. So we need to find an expression for AB, an expression for alpha AB, and an expression for omega AB. This equation can solve two unknowns, but we have three unknowns. So we don't know. So we need to find one of these things in order for this to work. So let us find, actually we have four unknowns because we don't know alpha either. All right, so we have four unknowns. We need to write expressions for two of them in order to use this equation. Well, let's take a look at the wheel. Point B is on the wheel, so if we could figure out the various accelerations, relative accelerations of the wheel, we could find the acceleration of at point B. So let's write that equation. So point B relative to the center point, which I'm going to call point O, which is fixed. So that's going to help. It has a zero velocity. So let's write that out. The acceleration of B is equal to the acceleration of O plus alpha crossed with RBO minus omega squared RBO. All right, so RBO is this distance. It's the position of B relative to O, so it's that distance right there. So we're going to go, the distance is 0.15, the radius there, right? And the first part, the I hat direction is going to be negative, and it'll be cosine of 30 I hat, and the j hat direction is positive 0.15 times the sine of 30, which is the opposite over there. All right, j hat. So that's our R. So we can write this out. The acceleration of that center point, which isn't moving, is 0. The alpha for this wheel is given, so that's plus 16 k hat, crossed with negative 0.15 cosine of 30 I hat plus 0.15 sine of 30 j hat, that's the R, minus omega squared is 8 squared times the R again, negative 0.15 cosine of 30 I hat plus 0.15 sine of 30 j hat. Okay, now here we know everything other than AB, right? None of these are unknown, so we can simplify this and get an expression for AB. If you plug all of these things into your equations, we need to take some cross products, right? So this is, let's look at the directions here. These are both negative, right? Because if you use your right hand rule, your thumb points in. So this should be a negative 16. This should be minus a negative 8 squared, so it's going to be positive. All right, so now we can take a cross product. Negative k direction crossed into the negative I direction gives you a positive j direction. So that's going to be 16 times 0.15 cosine of 30 j. All right, negative k crossed in with positive j gives us a positive I. So fingers along the negative k, so pointing inwards, bend them upwards to the j, and your thumb points in the positive I. So this will then be plus 16 times 0.15 sine of 30. All right, so that's the first term. This one we don't have to do cross products, right, because they're already set. So this is going to be minus 8 squared times negative 0.15 cosine 30 I hat plus 0.15 sine 30 j hat. All right, so we simplify this, we'll get AB is equal to 9.514 I hat minus 2.721 j hat. So we've found this one. Done. So now we need to find either alpha or omega. Alpha will come from this equation. Omega we can find from the velocity equations. So we're going to look at our velocity equations. Once again, we're looking for the omega of the bar, which will depend on the omega of the wheel. So let's start by writing the VA equation, just like we wrote the AA equation. So VA is going to be in the I hat direction, so VA I hat is equal to VB is a vector that we don't know, plus omega AB crossed with RAB. All right, we know that the omega AB is in the k hat direction, but we don't know its magnitude. So this is going to be VB that we don't know, plus omega AB k hat crossed with RAB. And RAB is written out here, so crossed with 0.5 cosine of 60 I hat plus 0.5 sine of 60 j hat. So if we do that math, then, well, if we're looking here, we don't know this, right? That's what we're trying to find. We don't know VB, and we don't know VA. So once again, we have three unknowns. We can get to two of those unknowns using this equation, so we need to know something about a third unknown. And the one we know something about is VB, because VB is attached to this wheel, and we know how the wheel is moving. So let's write that equation. VB is equal to, same equation again, we're going to use the center point, VO, which happens to be a center of zero velocity, not just instantaneous. It's always going to have a zero velocity. All right, so plus omega crossed with R of BO. Okay, so VB is what we're trying to find. Omega, we have a number is negative 8. And it's in the k hat direction, crossed with RBO, we have it written out here. So negative 0.15 cosine of 30 I hat plus 0.15 sine of 30 j hat. And if we multiply that out, do the cross products, we're going to end up with the cross product k crossed into I gives us a positive j, negative k crossed into j, positive j gives us a positive I, so that gives us 0.6 I hat plus 104 j hat. So that is our VB. We then know VB, so it goes in here, we can find omega AB and VA. Knowing omega AB, we plug it in here, and knowing VAB, which is in here, we can find alpha and A. So we're going to go on to the next slide and do exactly that. So let me give us some numbers here. This is equation number 1. This is equation number 2. This is equation number 3. And this is equation number 4. All right, so equation number 4, we found VB. We're going to plug VB into equation number 3 to find omega AB. So equation 4 into equation 3 will give us VA I hat is equal to VB, which was 0.6 I hat plus 1.04 J hat, plus negative omega AB times 0.5 cosine of 60 J hat, plus omega AB 0.5 sine 60 J hat. All right, so this was taking that cross product. Positive J crossed into, what was it? Positive K crossed into positive I gives us negative J. No, gives us positive J. That's that term. And positive K crossed into positive J gives us negative I, which is that term. And so now we can look at the I hat part of this and the J hat part of this. The I hat part tells us that VA is equal to 0.6 minus omega AB times 0.5 cosine of 60. The J hat part says that 0 is equal to 1.04 plus omega AB 0.5 sine of 60. From this bottom equation we can solve for omega AB, which gives us 4.16. You can also then solve for VA equal to 7.8, but we don't necessarily care about that. What we're interested in is VAB. So now if we go back up here, looking at our equation, we now have VAB, so we've got that one now. And we have VB, or AB, so we should be able to find these other two now, because we're down to two unknowns. So now we're going to look again at equation number 1 with equation number 2 plugged into it. So we get that AA in the I hat direction is equal to AB, which was found to be 7.114 I hat minus 2.721 J hat. And then we have plus omega AB times 0.5 cosine of 60 J hat minus alpha AB times 0.560 sine I hat. So that was the cross product of that term. So this was the alpha crossed with R term. Then we have minus the 4.16 squared, so that's omega squared, times R, which has 0.5 cosine 60 in the I hat, minus 4.16 squared, 0.5 sine of 60 in the J hat. Alright, so now we can break it up. We look at the I hat direction. We get AA is equal to 7.114 plus I hat over here minus alpha AB times 0.5 sine of 60 I hat. And this part is I hat minus 4.16 squared times 0.5 cosine 60 I hat. Alright, then we can leave off the I hats because we're breaking them out as I hats. In the J hat direction, we have 0 is equal to negative 2.721 J hat plus alpha AB 0.5 cosine 60, and then this one minus 4.16 squared 0.5 sine 60. From this first equation we can find alpha AB to be 40.8, and from the second equation, plugging in alpha AB, we can find alpha, or AA, the acceleration of point A, as negative 12.5. Units would be meters per second squared, and this is radians per second squared. So we used two equations over and over and over again, right? We used our relative acceleration equation and our relative velocity equation. We used each of them twice, once on the bar and once on the wheel for each one. And then we split them into I and J parts, and we were able to solve our problem. So let's take a look at some special cases in regards to acceleration. We looked at joined objects with respect to velocity, and we said that if they're joined together, then the velocity of point A is equal to the velocity of point A prime. right? Because they're fixed together. In terms of acceleration, however, what we can say is that the tangential parts of the acceleration are equal, right? So the parts that are tangent to the path are equal, but one would be accelerating in this direction, and one's going to be accelerating in that direction. So while the tangential parts are equal, the normal parts are not equal. The normal parts, right, the acceleration of A normal on wheel B and the acceleration of A prime normal on wheel C are not equal. They're actually in opposite directions and they have different magnitudes. So just keep that in mind. The tangential parts are equal, these two, but the normal parts are not. So the accelerations overall are not the same. Another special case that we looked at in terms of velocity are rolling objects. And remember, when things were rolling, we said two things. One was that the point of contact, if there's no slip, point A is an instantaneous center of zero velocity. This is zero velocity, not zero acceleration. Right? So that point may still be accelerating, even though there's no velocity at that instant in time. Point G travels horizontally, so the velocity of point G is going to be parallel to the direction that it's rolling. And so when we take our accelerations then, the acceleration of point G relative to point A, we've got the acceleration of G, acceleration of A, which isn't necessarily zero, tangential acceleration of G relative to A, and normal acceleration of G relative to A. Take our cross products, what we end up with is that AA, acceleration of A, is going to be equal to omega squared times R, and the acceleration of G is going to be equal to alpha times R. So this then is related here, and this term is related to AG. Let's take an example that makes use of some of these things, right? We've got a gear interlocked with another gear. We're pulling on a rope that's causing this gear to move, and that rope, we're told, is being pulled with a constant velocity. So we know that V dot is equal to 0 at that point, right? And so what we're trying to find, if it's pulled with a constant velocity, what are the velocities and accelerations of point A and B? So let's start with velocities. And this will be a review of what we did in lesson 2. So if we start with velocity, we've got velocity of B is equal to the velocity of point D. I'm going to call this point D. That is our instantaneous center of zero velocity, right? Because it is not moving, because the track isn't moving. So it's interlocked with the track's not moving, so the point there is also not moving. So we're going to use point D then, because that's an instantaneous center of zero velocity, so we have no zero velocity there. So this is just equal to omega crossed with RBD. What is RBD? Well, RBD is the position of B relative to D. So we start at D, we go to B, we went 2R to get to G, another 2R to get to B. So that's 4R in the positive J direction. Alright, so this then is equal to omega in the K hat direction crossed with 4R in the J hat direction. Positive K into positive J gives a negative I hat, so negative 4R omega in the I hat direction. Now, do we know anything about omega? We'll need to figure out something about omega, because omega is not, we're allowed to use V and R in our equations, but not omega. Alright, so how do we find something about omega? Well, we know something about the velocity of this point, right, which I'm going to call point C. We know the velocity of point C. We know something about we know the velocity of D. So knowing two velocities, we should be able to find the omega for this thing. So let's write out that equation. So velocity of C is equal to the velocity of D, which is still 0, plus omega crossed with R of CD. Now R of C respective to D, D to C is just 1r in the positive j hat direction. So this then is equal to omega in the k hat direction crossed with r in the j hat direction. Positive k to positive j gives negative I, so this is going to equal to negative omega r. So omega is equal to negative v over r. Alright, take the derivative of this, you get alpha. So omega dot is equal to 0 because there is no time derivative there, right? Because v dot is 0. And so this would be, let's add one in here, v dot over r, and v dot is 0, so alpha is 0. Alright, so now we know omega, we know alpha. That's going to be useful later, but for now we need omega. We can plug omega in up here. So up here, is that equal then to negative 4r times negative v over r gives us positive 4r. And the direction is in the I hat direction. Alright, so that is VB. That was one of the questions they asked. We now need to find VA. So VA is equal to similar equation. We're going to use VD again, instantaneous center of zero velocity, plus omega crossed with RAD. Well, RAD is this distance. Alright, so we're going to go in the negative I hat direction, we're going to go 2r. And in the positive j hat direction, we're going to go 2r. So we know what omega is. Omega is negative v over r. So negative v over r k hat crossed with negative 2r I hat plus 2r j hat. Do that cross product and we end up with negative 2v I hat minus 2v j hat. Alright, so negative k crossed into negative I gives a negative j. That's here. Negative k crossed into positive j gives a positive I. So this is a positive. Okay, so that is VA then. So those are the velocities. Now we're going to do the same thing for the accelerations. So we've got acceleration B equal to acceleration G, which is the center point of the wheel. There's no point in using point D for accelerations because there's nothing special about point D in terms of accelerations. It's got a zero velocity, but not necessarily a zero acceleration. The acceleration G, however, we will know something about, which we'll get to in a second. So, acceleration B equals acceleration G plus alpha crossed with RBG minus omega squared RBG. RBG is the position of B relative to G, so it's 2R, and it's in the positive j hat direction. So we don't know anything about, well, we know AG is in the I hat direction, so this is AG I hat plus alpha k hat crossed with 2R j hat minus omega squared, which we know omega squared, so that's minus omega is where? Here. Negative v over r, so minus v over r squared times 2r j hat. Okay, so that's that expression. We don't know AG, we don't know alpha, so, and we don't know AB, so we need more information. So let's take a look at AG. AG relative to the point C, which we do know something about the acceleration of point C. We know it's equal to 0, or the tangential acceleration is equal to 0. So AG is going to equal AC plus alpha crossed with RGC minus omega squared RGC. So if we look at this, we know that alpha is equal to 0, so that is going to be equal to 0. And we know that, well, we know RGC. RG C is equal to, so position of G relative to Z is positive R J hat. So we plug things in here. AC is going to be V squared over R J hat. Right, because AC has a normal part and a tangential part. So the normal part of AC is going to be V dot, normal part. If we look at, let me see here. So the normal part of G would be here in this direction. The tangential part of G would be in that direction. So this is going to be J hat. But V dot is 0. And then we've got plus the tangential part, which is V squared over rho, which is R. And that's going to be in the I hat direction. Okay. And then we have the alpha part, which is 0 minus omega squared. Omega squared is V squared over R squared times R. And so those cancel, and that's in the I hat direction. So we've got the positive I hat, negative I hat, they match. Those are going to be equal to 0. So what we end up with then is that AG is equal to 0. So whenever alpha is equal to 0, the center of the circle is also not accelerating. So this gives us then this equation up here where AG is 0, alpha is 0, all we're left with is this one term. So AB is negative omega squared R VG. Plugging things in, we get negative V over R squared times 2R in the J direction, which gives us negative 2V squared over R in the J direction. We can do a similar thing for AA. So the acceleration of A relative to G, so acceleration of G is 0, plus alpha crossed with R of AG, alpha is still 0, minus omega squared RAG. RAG, the last R we're interested in, is from A to G, so it is 2R in the negative I hat direction. So this then is equal to omega squared negative V squared over R squared times negative 2R in the I hat direction gives us 2V over R. 2V squared over R in the I hat direction. So once again, same two equations we used. Things simplify because we have things that are stationary, we have things rolling, so we know information about G, and in this case things were at constant velocities. So lots of zeros in those two equations, but the same two equations we used before that we worked through, and lots of math, but as far as which equations we're using, it's pretty straightforward, and lots of vector cross products.